Well, it looks like we're nearly there. Welcome back, everyone. And it's official. It's official. We're in week number 9. Thanks for making it in today, folks. I know it's kind of hard to make it back after getting through a tough midterms week, but we survived mostly. So let's get going with our announcements for today. We're going to finish off section 4.4 today. Then the next big move will be into section 5.2, working on mathematical induction. We'll spend some time in chapter 5 on this section and the very next section, where 5.2 is kind of like section 4.3, the one right before this one. 5.2, we're introducing what the technique of mathematical induction actually is. The mathematical concepts that we're going to be proving are kind of small and interesting, so that we can mostly focus on the proof technique, induction itself. And then we'll do another section like 4.4, we'll call it 5.3, just picking up more topics on induction, and also with the goal of looking into more applications. Induction is an interesting technique. For mathematics, it has its own purpose, but our authors also mention it plays an interesting role in computer science itself. Say, for example, you've developed some kind of algorithm. One of the things that you might want to prove before it's deployed is that it actually performs as indicated as you wrote that algorithm. One way you could give those proofs is oftentimes through an induction proof. So that's one of the major reasons why we're looking into this new technique outside of chapter 4. Aside from that, I have a bunch of announcements about the upcoming exam. Any questions or comments first before we get to those? Okay, well, our second exam is going to be next Monday. And with the weird confusion that we always have to talk about, if you're in section 04, then you're likely taking the exam in the classroom, and I didn't email you today. If you're in section 44, then you will have to take the exam in a testing center of some kind. Most people in the Pocatello Testing Center with some weird exceptions. If you're in that case, then I should have emailed you this morning. And if you're in either section and you're not sure where you should be for the second exam, don't hesitate to ask at any point. Send an email, stuff like that. I'll be very happy to direct you on what to do right away. But pretty much it's just going to be a complete rehash of what we did on the prior exam. Let me scroll this to the last spot. Oh, that's exam 1. Let's go down here. What I mean by a complete rehash of what we did on exam 1 is, well, we have the information that we're going to be working through right here, but also down below is the same formula sheet. Well, not the same one, but similar formula sheet, just like we had from the exam 1. This formula sheet is relative to these topics here. Then, just like on exam 1, this is a sample set of exercises, but you might find that some of them gave you major deja vu because these are the ordinary actual lecture notes now turned into worksheets where all of the extra information is just gone and you're focusing on answering the questions. So this is a great way to review for the exam, and you can go back to the Moodle website, just scroll to the relevant section to take a look at what the solutions were as we wrote them out. And for the folks who want new problems, extremely understandable, that's what this document is here as well. It's a brand new document. I'm writing out these solutions or these problems from scratch, so I also have to write out the solutions. So if you get going on this document, you might have to be patient and wait for the actual solutions to show up. It's the same kind of idea. I went on a section by section basis and just wrote down problems that looked like they'd be great exam questions. In either side of the documents, like say on version 1, you might notice that some examples are just not there. Say, for example, we go to maybe section 3.3, maybe not that one. Section 3.4, yeah, this is a good one to highlight. No, it's not. It's all there. Well, instead of just scrolling through these a bunch, occasionally you might notice an example just missing, and that was my way just to convey that example was great in class, but it didn't really make a useful topic in an actual exam setting. So some of those topics are gone, and that means this document represents the actual lecture note problems, which would make up an actual really great exam. And that's how I wrote the exam. I went to both of these documents, went from a section by section basis, these sections here, and just picked out representative problems. So this is highly similar problems to the real exam. So is the homework problems in these sections here. And same with version 2. This one might be a little bit tougher because I sometimes had to get creative to get new additional examples. So all those materials are there and available just as before. And I should pause right here. Any questions at the moment about the upcoming exam? Okay, other things I want to mention was, sorry for the folks who were really anticipating section 2.5 on functions. I tried to make it fit on the exam and it just didn't really seem like it fit in a great way. There wasn't a lot of actual concepts in that section. It was pretty short. And trying to throw it in just seemed like I was trying to make the exam bigger than it had to be. So we're skipping section 2.5 on the upcoming exam 2, which means I won't directly ask questions in section 2.5 on the final exam either. It wouldn't be fair if it wasn't on the second exam. And that means the exam is mostly just about logic and applied logic. 3.2, 3.3 is when we were getting started talking about propositions. Other interesting things were the logical connectives, the and operator, or operator, the implication, and so on. Logical equivalence, tautologies, and truth tables being some of the other interesting things we took a look at. 3.4 and 3.5 turns us around a little bit, and now we're just dealing with predicates, quantifiers, sometimes nested. And 4.3, we're just taking all of this information and applying it to writing out clever, convincing arguments or proofs. So that's pretty much what rounds out to exam 2. And like we mentioned before, right before going into exam 1, on Wednesday of this week, so the 12th, if you have questions relative to exam 2, wherever they come from, whether they're the homework questions, lecture note questions, or questions from the second document down here, shouldn't scroll like that without hiding the annotation. If you have any questions whatsoever on the 12th, I'm very happy to start off class addressing those questions, even if it turns into a kind of an informal review day. But I think that's the most amount of talking, or all the talking I need to say about these announcements. Any questions at all, folks, about, well, anything at all at this point, upcoming exam or otherwise? Yeah. Yeah, absolutely. For folks in Zoom, the question was, if you turn in 4.3, will I be able to grade it before the Monday? And that's absolutely true. That's pretty much the reason why 4.4 or 5.2 are not on exam 2. The turnaround's just way too fast. So if you get 4.3 in, even if it's not by the due date, let's suppose you submitted 4.3, maybe on Saturday the 15th. This is a busy weekend for me too, going into an exam. Even if you turn this into me on the 15th, online digitally, I'm going to make every effort to do all of my grading before the 17th. So I will get you that feedback returned to you. And honestly, I'm glad that you mentioned that, because really the most important thing you could do to study for any exam, not just this one, is not the actual review problems here or here. It's all about your actual homework problems that you did here. This is really major. Anything that you might have missed as a question, definitely come back to, take a look at, and see if you can see why you might have missed that question. That kind of review of going through your homework problems itself is really impactful. And if you're behind on any one of these sections, then far and away, the most important thing that will help you on exam 2 is just getting caught up on these homework sections before going into the exam. Like I mentioned, anything you get to me on Saturday, the 15th, that's a cutoff where I can guarantee I should be able to grade it and get it returned back to you. What other questions so far, aside from that one?
Yeah, so if you have like 4.4 due the Monday of the test, is it okay if we push that off so we can study for the test instead of worrying about it?
Yeah, absolutely. In fact, the due dates, they're kind of like a guide, right? Even if you turn this in on Wednesday, the 19th, I still accept it for full credit. But you know what? It just feels weird sometimes having a due date intersecting right on top of an exam date. So I'm glad you suggested that as well. Let's actually just move this. It's on the 17th. And let's push this to the 19th. Okay, it's official. Section 4.4 is now due on the 19th. And you got a great suggestion because it's kind of strategic at this point. If 4.4 is not on exam 2, then the best thing you can do to get a highest grade possible is to really focus on these. Then after Monday, return back to the other sections, getting back in gear, studying those problems. So I appreciate that comment. That's a great suggestion. And definitely in the spirit of what we'd be wanting to do for practicing on exam. Other questions at the moment? Okay, well, with those announcements and questions out of the way, we're now back to section 4.4. We'll move through section 5.2. And this is where we essentially left off last Wednesday. Not exactly. We finished example 1, we finished example 2. I think section 4.3 and 4.4 feels so different, it's good to just remind ourselves, what are we doing in section 4.4? Let's say that here and now. 4.3 was all about just the proof techniques themselves. So we try to make the mathematical concepts not too involved. So they're basic things like the product of integers are odd, stuff like that. In section 4.4, we want to do more proofs, nothing new in the proof techniques. But now we're adding the extra noise. If you're proving a fact like this about a bijection, we know what the proof technique is going to be. This will be a direct proof. The extra noise is we have to navigate through all of this technical information all at the same time to make that happen. So it's just extra practice with proofs when there's just a lot more going on. It's the idea in section 4.4. What we did was we took the definitions, we quantified them in a way that could help us navigate the way the proof should go. So we did that to both. Then we just ran through the proof. We had to show something was a bijection. So we first showed it was onto, definition above. Then we showed it was one-to-one, the second definition above. Then we asserted with a therefore, because we showed one-to-one and onto, original function was a bijection. So that's pretty much the idea with example 1. Same idea with what's going on in example 2. We're proving the theorem above that two sets are equal, set equality, if and only if we have two subset relationships. A is an automatic subset of B, and at the same exact time, B is automatically a subset of A. And when we went through all this information here, we found that, well, it's an if and only if. So we were proving a biconditional statement. This was the forward direction, P implies Q. And I forgot to add this to the notes. When we go next, this is the backwards direction, Q implies P. We showed both of those statements. That gave us the if and only if we wanted. And so now this tells us A implies B, if and only if we have those two subset relationships. And I mentioned this was just kind of a one-off type of proof. It was interesting because we're looking at the biconditional itself. That's the main thing about it. But our main use of that proof is we're going to use it on example 3 to prove this theorem down below. So this is where we get to the huge screenshot directly out of the course textbook. And this is in really a big spirit of what we said way back in the day when we were in section 2.2 dealing with set theory, and then just starting off logic in section 4.2. Everything that we see here are statements about the logical connectives themselves. But when you really look at this hard, you'll notice that there is something very strange going on. If you think of that tilde, that's the set complement operator, as a not operator, if you think that the union operator is an or operator, the intersection operator is an and operator, then what we're really looking at is just one of De Morgan's laws, which says the negation of P or Q is logically equivalent. We're showing set theory equivalence, so we'll use the theorem above to demonstrate that. Logically equivalent to not P and not Q. Matching up the and, the nots, and the or right here directly. What we really have going on here is something mathematically called a type of isomorphism. There's a mathematical system here with the connectives, a whole new mathematical system down here with the set theory. And if we can define a function from the set theory operations that goes into the logical connective operations, and if that function is a bijection, essentially we've translated from one theory into another, and we call it an isomorphism, meaning the structure of what we see with these logical connectives is the same exact structure as what we see in set theory. All that we actually changed was the symbols. Everything works out the same exact way. But to really demonstrate that, we're going to prove these ideas, that this law here from De Morgan And this law here from set theory, which is also called De Morgan's laws, it turns out, are one part of that isomorphism. So that's what we're going to do right here, prove the theorem. And I have a definition for the complement that I threw in, but you know what? We're going to need a couple more. So let's add a few more from our section 2.3, I think it was. First, any questions at the moment, folks, with the statement of the problem before we launch into its proof? Okay, so let's grab those things that we need from set theory. We have the complement defined here. I'm going to just mostly focus on the set definition, less on the words right here. We'll also need the union. So let's grab that operator. Wrong notes. This was way back in section 2.3. Now, when it comes down to unions, this is the essence of it. A union B means X is in A or X is in B. So we'll grab that, drop it into our notes just as an easy reference. And let's do one more. Intersection always also comes up. So when that comes up, we'll think of, let's see here, that definition. A intersect B means it's the collection of all X's such that X is in A, and at the same exact time, X is also in B. So grab that. And here we go, we're on our way. At this point, it seems plausible that there really is a true isomorphism going on here, because the union symbol we usually think of as an or. In fact, in the set definition, we literally put in an or to define it. The intersection symbol we often think of as an and likewise, we throw an and here in the set theory definition. Just like as over here, a symbol going this way is a logical connective, the conjunction, or and for short. And a symbol going this way is the logical connective, the disjunction, or for short. So it seems like these symbols really were defined in set theory in mind and vice versa. They pretty much match. One symbol just says this is about sets. The other symbol says this is about propositions, not necessarily sets. But now we're ready to get started on this. But remember, to prove set equality, the last theorem that we proved means we want to prove two subset relationships. We want to first show that the left-hand side is a subset of the right-hand side. Then, if we can reverse that, we have shown the actual equality in the middle, which would be analogous to the logical equivalence we see up here. This one was easier. We just needed a truth table to make that happen. So let's start by saying what we're doing, proof. And we'll begin by saying for first, the first part of the proof, we must show the complement of A union B is a subset or set equality. I'll just say subset for short, but write out the subset equals relationship. It's a subset of the complement of A intersect with the complement of B. So this is our first definition we want to get through. And because we're doing a subset relationship, you know what? Just to organize our thoughts, let's throw that in here as well. Where is subset? There it is. It looks like we're getting warmer. This will be just a really thin screenshot. There we go. Last concept we needed. Again, this was stuff from quite a while ago, so it's good to have it here to help us out. So to get started, if we're showing a subset relationship, that's what we're doing right here. It says, well, this relationship holds if every X in A is also an element of B. But the A here is this whole thing, so we want to pick an X in that location. Element of B would be that whole thing. So once we pick an X here, we need to say it's also in there at the same time. So that's the idea of the subset relationship. And let's do just that. Well, I want to do it in a slightly roundabout way. By first imagining, suppose X was an A union B, say what it means, And then insert the main thing we want to say, X is actually in the complement of A union B. So let's start off slow. If X is in A union B, that's not where we'll be, but this gets us started. Because now X being inside the union of two sets gets us to this definition right up here at the top. If X is in A union B, then this just implies, I'll write it out this way, X is an element of the set A, using our good old logical connective and, I'll write it out this way to say and, X is in B. Oh, but I shouldn't have said and. We should say, I mean, it's looking right at me. Should be using the or connective. Let me fix that one right away. That's a big fix. Let's use purple to really show that change there. So this is just a subset relationship. We just said X is in A or X is in B. But now we say where we really want X to be. It's going to be in the complement of A union B. So let's add to our sentence. So if X is an element of the complement of A union B, then we get to say this next new statement. Well, saying it's in the complement of A union B means it's not the case X is in A or X is in B. Let's write that out carefully using our logical connectives. If X is not in A union B, then it's not the case that X is in A or X is in B. Actually, this is a nice color for the logical connective since it's kind of making an unusual show here. So let's use that purple for the connectives. So we've got our not operator, which is just like the tilde operator we see here, but the tilde is saying you're dealing with a set. We're going to negate this statement and get something logically equivalent on the right. And here's how it goes. First, well, let's De Morgan's laws. If you're negating this whole statement, then you negate each of the portion that's connected with the or operator, and you flip or to and. So this is just a direct application of De Morgan's. So we would say X is not in A, and X is not in B. So if X is in A union B, we get to this relationship, but we want X to be in the complement of A union B. So if it's actually here, we negate that original relationship using the techniques from chapter 3. And this is what we have. X is not in A and X is not in B. Well, if that's the case, we can now say further. This shows if X is not an A, look at the complement operator right up here by the red dot. Complement of A means all X's in the universe for which X is not an A. So the moment we said X is not an A, coming back over here, we can say X is in the complement of A and back over here, but now we're talking about X not being in B. This means X is in the complement of B. So now once we get here, again, it's not a big step of what I'd done. I've just said if X is not an A, it must be its complement. And that's kind of how we started the proof. We started by saying if X is in A union B, we get one thing. Now say what happens when it's in the complement of A union B. We don't get that thing. But now, because of the and operator, we have an intersection, except we'll say it's the intersection of A complement and B complement. So in other words, therefore, we have a statement that goes, therefore, X is an element of, it's in two places at the same time because of the and operator connecting with this operator here. That's why we get to use the intersection and just say X is in the complement of A intersect with the complement of B. But that's what we want to show. Schematically, we grabbed an X. Oh, here, we did a bunch of logical work, definition work, and we showed, well, that X that came out of A union B complement ends up in here. The intersection of the complement of A and the complement of B. So that's half the proof, but I'm noticing my proof is starting to, or the theorem itself, starting to get hard to pick out. Let me put a break here. This is the actual theorem. The definitions are above. And now we can say, without erasing too much, there we go. This shows complement A union B. We want to show that this is equal to, but we at least have, it's a subset of complement of A intersect complement of B. We can reverse this logic, showing the subset relation goes the other way. Then we will have shown this equality right up here by the red dot once and for all. So that's our goal now. Reverse all the logic that we just saw here. Any questions at all, folks, with the forward direction, showing the subset relationship going one way? Okay, well, let's reverse this then. We want those subset relationships to go the other way. So let's say, next, we must show the complement of A intersect with the complement of B is a subset of the complement of A union B. So let's give this a try. And looking at what we did in the forward direction, it does convey some hints. So we might be able to reverse engineer what we have all here to try and change the direction. But I also want to make this completely accurate. Let me not forget subset or equals to should be in that relationship right there. That's a weird omission to not put it in. So let's start off as before. We pick an X from this set in the intersection. Let X be an element of the complement of A intersect with the complement of B. Now, once we're here, we should say exactly what this means as carefully as possible. So this means, well, X is in two places at once because of the intersection operator right here. We can say X is not an element of A and X is not an element of B. So the not an element of A is because if we're in the intersection, we're in both of these sets. So X can't be in A, it can't be in B as well, if it's in the complement of A and the complement of B. But now, apologies for the scrolling, let's grab these just briefly. Now we can use this information here, the definitions with the subsets, to see how can we go forward from that spot. X is not in A, X is not in B. But you know, thinking of that, X is not in A and X is not in B, that kind of connects with the union, right? Because if X is when it was in the union of A and B, then one of these would have had to have been true. Either X would have been in the set A, or it would have been the set B. This is an inclusive or, so it also includes a possibility it's both in the sets A and B. But we eliminated all of that the moment we wrote these two things out. If it can't be in A and it can't be in B, it can't be in A union B either. It had to have been in one of those sets. So this allows us to go forward one more step. This means X is non-element of, it can't be inside of, A union B. And this is where it gets exciting then, because when it comes to the complement, really for any element X, you're either in one or two places. You're either in the set A or you're in the complement of that set A relative to some universe. So the moment we said we're not in A union B, it immediately implied we have to be in the complement of A union B. Let's say that's right here. Let's just keep the sentence going. Therefore, X is an element of the complement of A union B. But that's what we want to show. We picked an X that was inside here. This time we didn't really say too much. It's kind of curious that the backward direction seems like it's a shorter argument. We made our argument and we are landed on X is inside there as well. And that shows the subset relationship. All that's left here is now conclusions. So let's see if we can make some reasonable conclusions with a small amount of space I have here. One conclusion you want to make is, well, we must show something. We should say we showed it, right? This shows complement of A intersect the complement of B is a subset of A union B as required. You don't have to say as required, but it's just a way to say we fulfilled some major objective on this side of the proof. And now going back, if we were to cite the theorem that we saw above, the theorem says set equality happens if you have a subset going this way, and you can reverse the subset relationship and show it holds going this way. We just did just that. So here's our big conclusion. Let's see if I can put in enough space here. I bet there's a way. Let's shrink all this down. Okay, with a little bit of shrinkage, we've got some extra space here. So now we can say, this work shows complement A union B is equal to, as a set, the complement of A intersect the complement of B. And finally, we did it, folks. This is the proof that De Morgan's laws, well, we showed just one of them, but that De Morgan law actually holds in set theory just as well as it does in logic. It's wild, though, because we've been constantly saying set theory is basically propositional logic with those connectives, like we've been saying. There's a mathematical isomorphism that shows their structures really are the same. Yet, showing this with a truth table is extremely fast and straightforward. It's just a process that you fill out. Whereas in set theory, proving any fact is this. It's a long, drawn out argument, and that's really pretty curious. The way your system is presented really imparts the way you compute and prove facts within that system is maybe a big takeaway with all of this. But we did it, folks. This was our last proof to round out chapter 4 before we get into other proof techniques going into, what was that called? Mathematical adduction in chapter 5. Any last questions or comments at all, folks, getting through our chapter 4? Okay, in my view, in my opinion, chapter 4 is the most abstract chapter in this entire course. And chapter 5 feels like it's worse at first. But part of my goal of chapter 5 is to convince you that what you're doing when you're making a proof by induction is something really very natural in a certain sense. Induction proofs have a lot to do with the concept of recursion, and that kind of concept comes up all the time in coding. So we're going to first in 5.2 really just attack the mathematical problem of what's induction. At 5.3, we'll pick up a couple more techniques, but then also turn to applications at the same time on how does this kind of work connect with coding and computer science. So first, let's get started, section 5.2. And here's how it starts. A wall of text, apologies about that, we'll get through it together. So this here is an algorithm that our author puts out on any proof by induction. Felt like it was pretty helpful. He also has drawings and schematics that you could take a look at into the reading. Above is the whole definition of proof by induction. This is all you have to do, 2 steps. But understanding what you did in those 2 steps is not easy. And so another way to view this is from a whole different textbook, from this book, 4th edition, is when you're doing a proof by induction, it's some kind of proof machine really that you're working on. This kind of view is really pretty helpful because it says schematically, what in the world are you actually doing in a proof by induction? But looking at all this is really very vague until we prove our very first statement through induction. So that's our goal. work through this definition really very carefully. The screenshot here is just more for your reference on a great way to break down each part of the proof. Then, once we prove the statement down here by induction, we'll try to take a look into what we just proved through the view of this idea, and then just prove several more statements. The homework problems relative to this section aren't too long. I have 3 proofs by inductions for you to take a look at. And here on these notes, we'll do 4 different proofs as well to give us a lot of different views and angles on how some of these proofs can go. So let's get started. Here's the definition, but we're going to be scrolling as we go. So let me copy this and we'll take it along with us. Well, let me copy it as a screenshot, actually. Okay, so example 1, this is the mathematical statement we'd like to prove. And it's a pretty curious statement. It's not like proving product of integers are odd or even, things like that. It's saying if you take 1 plus 3 plus 5 all the way to 2n minus 1, but hey, that's the structure for an odd integer, 2n minus 1, the sum of the n first odd numbers is somehow, some way, n squared. Weird little fact. If we can prove this through induction, then that's probably about the slickest proof ever. Not saying this is the only way to prove it, but for something like this, which kind of naturally leads into an induction proof, sometimes it takes a lot of creativity to give some other kind of proof. So we're going to go directly through induction. So let's read through this definition in earnest. Suppose we want to prove that Pn holds for all n in z bigger than or equal to 0. I should say right away, the z bigger than or equal to 0 could be z bigger than or equal to 1. That's what it's going to be in a lot of our problems, like we see here. 0 if it makes sense, or even something like 5 if your statement only occurs as true at integer 5 and beyond. So the value above here as a superscript is not as important as the set z itself, meaning we're dealing with integers now. But we have a statement, P of n. That means there's a predicate function behind all of this. It's not a bad idea to start with the actual predicate function. So it says for every integer n, we have a statement. So we can now say define the predicate P of n. Once we give it a value of n, where that could be 1, 2, 3, 4, 5, and so on, it becomes a proposition, which is either true or false. That's why it's a predicate. Its value, truth value depends on n. And it's just a statement that this equals n squared. It's a clunky statement to write out, in all honesty. But no harm writing it all out if you prefer. If we wanted to, though, we could include an extra level of abstraction here. Go back to section 2.2, this is like week 1, and use summation notation. Instead of saying 1 plus 3 plus 5 all the way up to 2n minus 1, you can really compactify our work, focus on the necessary elements, and write it out this way, xi. So summation from n equals 1 to something, xi. The xi would be this right here. So let's say our statement is really that the summation as I goes from 1 to n of the structure to n minus 1 is equal to n squared. So all I've done is collapse this whole thing into one big summation, assert it's equal to n squared, so it's the original statement. So we've got a predicate that was this part of the induction, and we want to give a proof of by mathematical induction of this statement. So quantifying naturally comes up in this kind of context, quantified over the integers greater than or equal to 1. Now let's say that's right here. We want to prove this quantified statement that for all n in z greater than or equal to 1, P of n. So what I'm saying here, P of n is true, that equation would really hold as true. And this is going to work for all integers n. Usually when you see a statement that goes this way, you might be thinking to yourself, this is proof by cases. And that's a pretty good analogy. But we're only doing two cases. We're going to show the base case or the basis case. That's P of 0. And then for P of 1, P of 2, P of 3, and so on forever, that will be the inductive case where we prove an implication. But at least we're on the right track. We have a statement we want to prove that's fully quantified. We know what the predicate is, and this really helps us organize and direct what should all the next steps actually look like. So this is like the initial analysis. If you didn't write any of this in, you wouldn't lose points on your homework assignment. I encourage you to write in this extra filler material because your subconscious is solving the problem and you're organizing how the solution should look when you do this extra effort. But now we're ready to start. We'll call this proof by induction. It's very common to say proof by induction because this is a specific proof technique. It allows the reader to know exactly what you're doing on each step. But if you didn't say by induction because you're doing a homework assignment and you understood that's just what every single one of these are going to be, that would be okay. I'd understand. Might feel a little bit redundant. In the proof by induction, we start off with the so-called base case. We need a ground, a foundation, something to anchor this whole statement to. In other words, if we can't show that it holds at exactly n equals 1, we've got nothing going on whatsoever. And that's what we're doing with the base case. It may not be P of 0, it might be P of 1 like in our problem, but whatever the value is here, it comes from this value. When we said for all n and z greater than or equal to, whatever that value is, informs us of the base case. So let's start by saying step 1, we must show P at 1 is true. Where that 1 again matched up from this 1 right here. And just writing out what the P of 1 statement is usually how the base case goes, step 1 in this proof. Well, if the integer I was 1, we wouldn't have all these prior terms. We would just drop 1 directly right inside there. It's also honestly a little easier to see in the summation formula. Let's say if n is 1, let me start over. Okay, back to that. If n is 1, then I goes from 1 to 1. So I replace the upper limit of summation up here to n minus 1. So if we go, hang on, let me fix my indexing. I made one mistake right here. I carried down the formula 2n minus 1 directly down inside here. But if the index is I, that should have been really a 2i minus 1. Sorry for that error in that location here and here. Let's fix them both. So that should be an I. And that should be an I as well. Does that make sense to folks on what the error was and what the fix is? Okay, weird distraction. I was looking at the nth term of this formula and just dropping it down in. I should have looked at this a little bit more clearly on how these structures should really go. But now that I is 1, this is where I noticed my mistake. You plug in the value of the index I to where it occurs right here in the formula. We would just get 2 times 1 minus 1. Might as well highlight that as well, which gives us a value of just 1. So that's the left-hand side we're looking into. Now, to show that P of 1 is actually true, we take n as 1 and throw it into the right-hand side. Let's just say that by saying n squared becomes 1 squared equals 1. So we were looking into P of 1, but when we evaluate the left-hand side, we get 1. When we evaluate the right-hand side, we get 1 as well. And this is enough for us to say right away, this shows P of 1 is true. And the base case is complete. That deserves an exclamation mark. This is just our very first proof by induction. And now we are ready for the inductive case. But first, it's good to spend some time right here on step 1. Any questions at all, folks, on what we wrote out here? Okay, well, what are we trying to show in the inductive case? This is where the magic in proof by induction happens. It's usually the most confusing case. It's hard to know what we're really trying to say unless we focus on that. This is the logic of proof by induction, and this works for n greater than or equal to 1. So for our problem, if we started at 1, this would be for every n greater than or equals to 2. We've already shown the one case. We're moving on to every other case. And now what it's saying is, if n is arbitrary, and all we know is that it's bigger than 2, we can show that the truth of Pn minus 1 implies the truth of Pn, then we'll show that the predicate Pn is true for every integer n and z greater than or equal to 1. So this is the magic. And one way to view it is, if you did show that part right there in green as true, then because we showed that P of 1 is true, it itself would imply P of 2 is true. Because what this is saying is the prior predicate, it's a predicate when you plug in a value, it's a proposition, making it kind of confusing. The prior proposition with the value of n minus 1 thrown in will imply the next proposition where n is 1 higher. So if I prove this already, and we just proved P of 1, we've also proved P of 2. And we've also proved P of 3 because we take this, put it back into this. P of 2 being true implies P of 3 is true. And this goes forever. We sweep out all integers greater than or equal to 1 because this just does not stop. This implication will hold for every single proposition in the overall predicate right up here. Well, that's one way to view it. Any questions about that, folks, before we go to really write out the inductive case itself? Okay, let's give this a try. I think to focus on really carefully on the inductive case is not every author writes this out the same way. It's kind of surprising, and it's really unfortunate. I think our author picked out the best way to write this. Some authors go show P of n. Let me fix that P. Show P of n implies P of n plus 1 is true, and that's completely equivalent as a proof technique as well. The reason I like the way the author is showing this, Pn minus 1 implies P of n, is because once you write down Pn minus 1, you'll do some work, but then your goal is to get back to Pn. Well, that's just this original statement. So it makes the original statement of the problem your goal and your target. You'll always know what you're going for because you've been looking at that statement this whole time and that work on this proof. So that's the idea. We're going to start by assuming Pn minus 1 is true. For all n greater than or equal to 2, we showed it's already true at 1. And so now, here's how the next step goes. Next, assume P n minus 1 is true for some n bigger than or equal to 2. Bigger than or equal to 2 again because we're going 1 higher in the base case. Let's get some extra space going. If we assume that Pn minus 1 is true, let's say exactly what that would mean. Here's the Pn statement right here. So keep your eyes on this box. And we can say, this means that the summation as I goes from 1, not up to n right there, it's going to n minus 1. So that summation from I equals 1 to n minus 1 of the same structure, the odds 2i minus 1, will be equal to not n squared, because this time it's going to be n minus 1 squared. Okay, so in green, this is assuming that the predicate Pn minus 1, this one here, with n minus 1 dropped in that location, and that location, is actually true. We're going to make that assumption directly. Any questions at all, folks, with this assumption here? Okay, using the truth of that assumption, we now need to show it implies directly Pn is true. So let's say that's right here, just to be specific. We must show this implies Pn is true. That's not as a complicated statement to write out because we wrote it out right here at the very, very beginning. So if we could get to that structure, we will have proved the entire formula right here. For all integers n, this is a valid formula. So let's give this a try. The statement of P of n begins as a summation as I goes from 1 to n of the structure 2i. So we can write in this part. And our goal is to show that it equals n squared eventually. So this is the goal or the target. This is essentially where we're looking to at every algebraic step we take going this point forward. So the truth of Pn says, let's not use that color just yet. Let's just say, how about we have, I think that's a good way to start. We have that, thinking of the Pn summation, I goes from 1 to n, 2i minus 1 equals, and this is where we get into the algebraic side of all this. Here's where we're doing some math, substitutions, possibly some FOILing, that kind of stuff. But this summation right here can be thought of as relating to this one. Only difference between the one in green and the one we just put down is the one in black has one extra term. If we walked it back by one term, we would reveal that structure there. Let's do exactly that. This sum can be now rewritten as a summation as we go from I equals 1 to n minus 1. So we're not doing the total sum here any longer. We're doing almost all of it except for the last term. Still for the structure 2i minus 1. Add to that, what will you get when you take n, plug it back inside here? That's the last part of the sum that we didn't directly use. So the final term is 2n minus 1. Actually, at this time, not the thing that we tried to correct as an I, because now we're plugging in the last part of the summation n, and it directly places the I in the index of the summation. So now that we've done that, keep in mind our goal is to try to get to n squared. That's our main target. And we have a big jumbled mess, but a humongous amount of mathematics is substitutions. And here's one substitution already. That goes in right in place of that. Because we were just calling Pn minus 1, we assumed it's true, and it is that, n minus 1 squared in summation. So with that substitution, we get n minus 1 squared. Let me actually drop the yellow. That looks kind of hard to read on my screen here. So just a direct substitution plus 2n minus 1 gets us to this result. Now, if we can expand this out, do some algebra, with always keep in mind, look into the target, trying to get n squared, we'll see if we got close, if we missed something in this proof. So next line. At this point, I think we need to carry this to the next page. So let's expand out the n minus 1 squared to get n squared minus 2n plus 1. Copy in the plus 2n minus 1. And there we have it. The terms cancel in a kind of surprising way. It's like a mathematical miracle. Somehow, some way, we made that last substitution by factoring the sum, while splitting the sum as all the terms up to the penultimate and the final term, spanning all this stuff out, and we've got the n squared we really wanted. So what did we just show? We showed that if Pn minus 1 is true, then Pn itself must be true. Let's say that here. Pn started with the summation, ends at n squared. So we get to make a conclusion here. This shows Pn is true. That was the inductive case. Let's pull up that definition now that we're at that stage. The deductive case was prove that the prior n minus 1 value, if it's true, and we assume it's true, we'll conclude that the next value, P of n, must be true. That's where we got to. So we can now say this completes the inductive case. And what more do you want to say at this point is kind of up to you as a stylistic choice. You could say the proof is complete. You could say we show this fact here by mathematical deduction. Really kind of up to you. I think kind of the nicest way to say it as just an overall summary is that, let's make this a new paragraph. This work shows 1 plus 3 plus 5 plus 7, all the way on to the nth odd number, which is defined as 2n minus 1, is just n squared. Impressive in a way that the sum of the first n prime numbers is automatically the square of that number n. I don't know how you would show this fact directly, but by induction, it has to be true. There's no other way of getting around this. So let's say by induction. And even though the formula itself, it wasn't too hugely revealing mathematically or anything like that, but you can now imagine that in place of that formula, it might be some kind of script, maybe in Python, who has a specific purpose to do something and it iterates across integers. A very natural thought you might have is, can I prove that that script really does what I think it should do? It's an honest proof by induction in itself, in a certain sense. So that's the immediate takeaway or application to this kind of work. Thinking of proof by induction is just a great way to think about algorithms themselves. And when we get more information about induction, we'll talk about how this all connects with recursion as well at the same time. But let me see if I can scroll out. Here is the whole statement. The thing we want to prove, they're rewriting it as a predicate and quantified, then the basic case and the inductive case. Any questions at all, folks, with what we've got so far? Okay, to me, the harder elements about this are what's color-coded in green, trying to show the substitutions. If you can wrap your head on how we're taking the assumption, assume Pn minus 1 is true, and work it together to show P of n is true, that's how it was in the color coding. That's the hardest main difficulty about mathematical induction. Let's see if we can take another look at another problem while we're at this. Might as well take that with us as we go. And let's drop that down below here as if necessary. And then maybe one last statement. or thing to think about with proof by induction. This is what we literally did in the problem that we just completed. We showed that P of 1 is true. Then we also showed this. We did it in a slightly different way. Remember, the authors have different points of view. We showed Pn minus 1 is true. The proof machine is just a silly thing that we did. We showed that there's an actual implication that connects this way, and we showed that Pn is true. Again, some authors go Pn to Pn plus 1. Our author goes Pn minus 1 to Pn. It's the same exact technique. It's just re-indexed, essentially. So what this thing does is, after you've proven P of 1, if you can prove the so-called proof machine, this is the inductive step, then you take P of 1, feed it into the machine. It'll tell us P of 2 is true. You feed P of 2 back into the machine. That's what's being said here. Outputs P of 3 is true. And this is how we show that for all n in Z greater than or equal to 1, P of n, meaning P of n is true if we just write down P of n. So that's the whole idea, just a different way to think about mathematical induction. If you like arrow diagrams, this is exactly what we did in the last proof. Well, aside from that graphic there, here's the next thing we'd like to prove. For every integer n in Z, if you take the sum of the squares of all those integers up to n squared, it becomes that. Kind of weird. You might have seen this if you were digging deep, looking into calculus, doing an integral, evaluating a Riemann sum. These kinds of things come up before you get to the fundamental theorem of calculus. Weird summation techniques. So we want to prove this thing here and now. Here's how it'll go. Well, first, let's do some surgery on this. This is the overall statement, as clear as it can be written, possibly. But for the purpose of the proof, it's a good idea to compactify this. So let's rewrite this as a statement. P of n is the statement that, instead of putting in this right here, let's throw in the summation. If we sum from I equals 1 up to n, avoiding the mistake, I will not put n squared there. We have to put in I squared to avoid that same mistake. It should come out as n times n plus 1 times 2n plus 1 divide by 6. Who came up with that is a really interesting question, I think. But at least we get to do the proof of this statement. Well, what we're really proving is that for all n in Z greater than or equal to 1, greater than or equal to 1 coming from up here, the original statement, P of n is true. So that's what we would like to prove. And here's how it goes. Step 1, we need to show that P of 1 specifically is true. So we call this the base case, or basis case if you prefer. Show P of 1 is true. Okay, proof is written in a slightly different way. We said P base case instead of step 1. And we're just being really terse, saying what we want to do. If we're going to show P of 1 is true, then we'll say, if n is 1, then look into both sides of the formula independently. First, there's the left-hand side of the formula, and we can say summation I goes from 1 to 1. Again, that looks weird. We usually wouldn't use that summation for that kind of sum, but we're just directly using this formula here. We're plugging I squared in to complete the formula, then plugging in just 1, giving us a 1 squared, which evaluates to 1. And so that's what we get on the left-hand side. Right-hand side had better be exactly 1 as well. If not, well, proof is over. This was a lie, not a mathematical fact. So let's put in 1 here. But first, let's start by saying what we're actually computing. Take n plus 1, 2n plus 1, 6th, Now use this information, if n is 1, that the structure on the left becomes 1 times 2 times 3, divide by 6, and that is 6/6. Hard to say for some reason, and that's exactly 1. That balances the equation, so we just showed P of 1 is true. Left-hand side is 1, right-hand side is 1. We just need to say that. And this shows P of 1 holds. Well, we're done, folks. That's the entire base case. But like we mentioned, oftentimes that's the easy part of all this. The inductive case is where a lot of the thinking and mathematical fighting and sometimes a lot of algebra actually happens. And that's the so-called proof machine. In this diagram here, if this resonated with you, we're trying to connect P of n implies, Pn minus 1 implies P of n is true. So let's call this the inductive case. And in the inductive case, we show Pn minus 1 will imply, let's put this in blue, this is our target, Pn is true. So we've got what we want to do. Next thing we need to do is actually write this all out. But before we actually show the implication, we should show what does Pn minus 1 look like as a statement. So we're coming back over here and just rewriting it out. Let's say here, Pn minus 1 is an entire statement that evaluates to true or false. But keep in mind, we're throwing in n minus 1. So 1 changes up here on the red dot. It's a summation as I goes from 1 to n minus 1 of I squared. And it changes all the values here. This will be n minus 1. This is n minus 1 plus 1, so just n. And this one is annoying. Let's work this out really carefully. 2n minus 1 plus 1. For some reason, the algebra is not too involved here, but if I do this into my head, I have like a 50-50 chance of making a mistake here. So this is 2n minus 2 plus 1, which gives us 2n minus 1. So 2n minus 1 would go here, then divide by 6. So that's the whole entire step right here, whole entire statement, Pn minus 1. We need to take that and show that the truth of this, we're assuming that this is true, implies P of n. Let's maybe be just a little bit more specific. Pn minus 1 is that statement, and we assume it is true. Well, now back to P of n. We're trying to prove that the statement P of n itself is true. So that means we would have to write out this whole thing. Let's write that out and say, next, P of n is the statement. I think this is the part of the proof where I have to admit I need more paper space to actually fill out all the details. Okay, so let's put it here. And now say P of n is the statement that summation, I goes from 1 to n. Oh, let me say it slightly better. Summation as I goes from 1 to n, I squared equals n plus 1, 2n plus 1 over 6. And we must show this is true. So those are the next steps we would have to take. Any questions so far, folks, to this stage? Okay, I'm looking looking at the clock here and realizing I've kind of painted myself into the corner. Let's write out what these next steps would be. I don't have enough time to really go through it in a nice way without just racing through it. So I'm going to leave this on the next steps, and we'll come back and complete this proof next time. Does that sound all right to folks so far? Okay, so here's how those next steps are going to look like. We would take this whole thing right here and go where the red dot is. We have I goes from 1 to n, summation, I squared, so the sum of the first squared integers. We need to show that this equation holds, but I really can't go in any direction forward unless I use the prior knowledge that that formula actually holds. This might feel like deja vu from the last problem. It means we can split up our sum in this way. Go from I equals 1 to n minus 1, summation, I squared, because we actually know what that value is going to look like. And then the last term on this summation is going to be plus, take n, drop it inside the formula to get n squared. Then the next step, this is where the algebra actually becomes kind of prohibitive. It takes a little bit of time to show this. But the next step is all of this by substitution becomes that structure up here. Let me just reorganize n times n minus 1 times 2n minus 1 over 6 plus n squared. At this point, this is algebra, but there's actually a good amount of algebra to show. You might be able to get this done depending on how fast you can expand this, add the fractions together in 4 minutes. But that's pretty much what my next steps are going to be. We'll do a whole bunch of algebra right here when we come back on Wednesday's class and show that we actually end up here, n times n plus 1 times 2n plus 1 divided by 6. Once we get there, that's the inductive case, and the whole proof is done. We've created at that point an essentially a proof machine where once we've proved P1, the conclusion of this inductive step will show Pn holds for all n. Well, where n is an integer greater than or equal to 1, of course. But sorry, folks, this one was a interesting one. I thought we could get a little bit further in the algebra, but I'm reminded this one's not as friendly. But any questions at all, folks, with where we're at with induction, where we're at with this problem, or otherwise? Okay, this will be a good stopping point for us then. When we come back on Thursday's class, I'll take any review questions that folks would like to discuss relative to exam 2. Then we'll go back into these problems and finish out the last, it looks like 2.5 remaining proofs on this document. But have a great night, folks. Congratulations again on getting through midterms, and I'll see you all next Wednesday.